Okay, let's get this over with so I can send you on your little holiday. But I'm going to remind you that you're supposed to be reading and studying. So at least do some reading and studying while you're on holiday. And 31 degrees tomorrow it's supposed to be. So bring shorts home. Yeah, I know. Bring shorts home with you if you're going home. Okay, so soft introduction to neural networks. I barely got to neural networks with the class before this. So let's see how far we can get with you guys. Maybe now that I'm practiced up, I can do a little bit better. Okay, so before I begin, I'm going to define a set of notation. Don't worry if you don't understand this. It's going to become a lot more clear as I introduce examples, right? So what I want to do is collect a bunch of data and assign to that data a label, right? So I think I skipped this slide. Yeah. Before I begin anything, right, I'm going to teach you a little bit about machine learning and artificial intelligence and neural networks, right, which are just sexy new buzzwords for applied statistics. Right? These are strategies and algorithms we've had since the 1970s. They've just somehow developed a new, I don't know, new sexy names means that everyone's super excited about them. But when you hear neural networks or machine learning in your head, I want you to think applied statistics. Then everything becomes a lot less magical. There are two types of machine learning, right? Supervised machine learning and unsupervised machine learning. Supervised is easier. Supervised is what we're going to be talking about today. Supervised means that you've gone and collected data from the field rather than asking the computer to learn arbitrary characteristics on a data set. So we're going to talk about linear regression, that's fitting a line to a scatter plot, logistic regression, that's separating points on a plane, and finally neural networks, which is like a combination of the things before it. So as I was saying, I'm going to define the notation that I'm going to use for the entire talk here. Okay? So I want to collect some input. And this input is going to come from an n-dimensional feature space. N-dimensional just means you have n many values, a vector. And I'm going to denote the ith input or the ith data point as the vector x with this bracketed I, just to distinguish it from an exponent. I'm going to further let the ith input have a label called yi. Right? So you should be used to this, right? X's are associated with y's. Then I'm going to collect all of that into a set called D, which I'm going to call my data set. So the data set is going to be pairings of inputs and labels. So that's all you really have to keep in your mind. Then we have X, inputs, and Y, labels. So here's an example for linear regression. So we could go out into the field, and we could collect information about house prices. And I can collect two features, in this instance, the square footage of the house, the age of the house in years, and its value. So in this case, the two features are square footage and age. The inputs are the pairings, 1517, 3004. The labels are 150 and 2100. And the data is just all of that collected into a set of pairs. This is the statement of the problem that we want to solve. Given some data, I want to learn parameters to a function. And in this case, the function is just going to be a hyperplane, right? A line on the plane. And I want this function, right? I want to get a new function which, given input for some house that doesn't exist, I want to estimate what the value of a house with this square footage and this age would be, right? I want to learn a hypothesis function which is going to do that for me. It's called a hypothesis or prediction function because it's predicting or assigning new labels. So for example, we could go into the field, we could collect a table of data, we could go and learn a hypothesis or a prediction function over that table, and then we may give it a new question. I can say, well, how much is a house with 2,000 square feet that's 5 years old worth under this weighting? Well, then it may say 300, right? But it also may be the case that the hypothesis function we train is going to be off, right, for already known quantities. So we may train a hypothesis function on this table which says a house that is 1,500 square feet and 17 years old is worth $200,000, right? So our hypothesis function that we're going to train is going to be imperfect somehow, right? It's not even going to go through all the points in the evidence that we've collected. This becomes a lot more clear when I show you pictures. You may be more familiar with this problem, right? Given a scatter plot in R2 on the plane, find the line of best fit. Who did this in high school? Anyone? Congratulations, you've all done machine learning already, right? This is a basic machine learning algorithm, right? What are you trying to do? You're trying to learn the y-intercept and the slope of a line that somehow best fits this collection of points. Okay, but what does it mean to best fit a collection of points? Oh, one addendum. To make all of our mathematics a lot more easy, I'm going to assume that that point in the middle there is 0, 0. Right? That the line goes through the origin. And because the line goes through the origin, we can get rid of the y-intercept. Right? I don't have to learn 2 parameters, I just have to learn 1. Right? So by putting it through the middle, right, all we have to do is learn the slope. Right? So what I'm saying learning for this example, what I mean is we're going to try different slopes for this line, and we're going to see which slope corresponds to the best fit. Okay, so in order to have a line of best fit, we have to know what it means to fit something poorly. Right? So let's skip this. Right? So, and let's skip this. Okay, so this is how we can quantify error for choosing a line. Right? And this is called the quadratic loss function, and this is the easiest way of defining error. So the pink line here is our hypothesis. That's the line of our current line of best fit, or a candidate for the best fit. And I'm going to define the error like this. You set your line, right? So the points that we are guessing are these black ones, right? We're saying, okay, so for here on the axis, our guess is going to be there, but perhaps the true value is here at the blue. So what I'm going to say is the error associated for picking that line for that one point is the distance to the line squared. So there's 3 ways I can say this. I can show it like this, where it's like, well, the error is just this distance. I can say, well, for the jth data, we have this guess. That's y hat is our guess. But the true value is yj, the label. So the error associated by choosing this line is just the squared difference between the data label and our guess at the data label, right? Squared. Or using the most amount of notation, which is the one that I have to use. Remember that this pink line here is an equation of a line. And we've given this equation of the line the name h for the hypothesis function. And h gets x1 and theta 1. Theta 1 is the slope, and x1 is the free variable. So in order to find this point, if you give me a data point, the ith data point, I give it to my hypothesis function, it returns a y point, and then I take the difference between that and the true label. So basically, if you've missed all of that, the error associated with choosing a line through a set of points is the accumulation of all of the distances between the point and the line. Okay? So that looks like something like down here. Okay? So you're basically just accumulating the squared differences. And if we, so I'm going to use the notation that the data scientists use. They call this cost function j. Don't ask me why, right? So when I use j, just think in your head cost function, right? So if I'm able to then say, well, if you set the slope of this line to 2, you get this error. If you change it to 3, you get this error. Then it just becomes a game of finding the slope which generates the least amount of error, right? And there's something very special about this quadratic loss function. If I work it all out, right, I can just write the definition of cost. It's just the sum of the square differences between our guesses and the actual inputs. Well, our guess is actually just the result coming out of our hypothesis function, which in this case is just the line. That's the line. Minus the true input squared. If I expand that all, you get this. Now, if you think about what this means, okay, the x's in here and the y's in here are going to be numbers, right? I have maybe 1,000 of these xy pairings, so I give all of this to Python, and it returns to me a polynomial in theta, right? The only thing I don't have set here are thetas, right? So you're going to give this to Python. It's going to come back. It's going to say, here's a quadratic polynomial. It's 2.748 theta squared minus 1.6 theta plus 10.9. Right? You'll get an honest-to-God quadratic polynomial back. And polynomials look like this. Right? So I can draw the cost function. For that line fitting problem, if I plot the cost associated with choosing a theta, it looks like this, a parabola. Okay? Where is the minimum error? Error is on this y-axis, right? The theta I'm choosing is on the x-axis. Where is the cost minimized? For God's sakes, it's not a trick question, right? There, that minimum, it's at the bottom, right? You can minimize curves, right? The least value this curve has is at the bottom of the parabola, right? So there's a technique I want to teach you called gradient descent. So imagine you take a ball, right, and you drop the ball into the parabola. What's going to happen? It's going to roll back and forth like this, and then settle on the bottom here, right? That's basically gradient descent. I can mathematically model, right, the physics behind that, but it's actually way, way easier than that. Here's how you can find the bottom of that parabola. Given the equation for a parabola, here's how you minimize it. Each of you should already be able to program this. Pick an arbitrary point on the parabola. Okay, that one. Find the slope. Use calculus to find the slope. Oh, well, the slope is positive. Okay, move left. Find this, so move left on the curve. What's the slope now? Oh, the slope is negative. Okay, then move right. Slope is positive, move left. Slope is negative, move right. Okay, then eventually you'll converge. That's all it takes, right? Bonus, move proportionally to the magnitude of the slope. Right? If you're really far out, the slope is going to be near infinite, and you're really far away from the minimum. At the minimum, the slope should be 0. Right? So you should be finding that your slopes are gradually getting smaller. Right? So that means if your slope is enormous, you can move left by a lot. Right? So anyways, yes? With higher powered mathematical techniques that we're not going to get into. Right? Well, my answer to that is use more calculus. Right? And my secondary follow-up would be finding a local minimum isn't that bad. Right? If it's working, it's working. Right? We're not making any guarantees that this is the absolutely best hypothesis function. Because we could choose different error functions, right, which minimize against a different error, which may give better results. Right? So, but for this particular one, you're going to get a quadratic polynomial back, which is going to necessarily have a single local and global minimum. Yeah. Okay, so, but I simplified the problem quite a bit. Right, I said, okay, let's not train a real line. Let's just train a line by rotating it. So what happens if I want to go back to the old problem of saying I want to train an honest-to-God line, which means that I both have to find how it's turned like this and how it's shifted up and down. I have to learn 2 parameters. Well, the cost function gets more complicated. Right? The cost function is now in 2 dimensions. Well, 3 rather. But it's still convex. I can make the same argument. I can show you, well, this is actually just another quadratic polynomial of higher order. But the property that we require is still there, right? That if you take a ball and you throw it into the surface, it's going to find its way to a local minima somehow. Right? And we can model this sort of physical property using calculus again. So who knows what a partial derivative is? No one? Okay, you took physics, I guess. Right? Or maybe higher ordered math. So you can find slope on a curve. It shouldn't be a surprise to you that you can also find slope on a surface. But slope on a surface is a little bit different because you also have to give the direction of the slope. Right? There's only 2 directions on the plane, left and right. Right? On a 2D surface, you can sort of say what is the derivative north and what's the derivative east. And that sort of gives you the derivative, right, as a vector. So you can play out the same game on this as we did with the parabola. You can pick an arbitrary point on this surface. Let's pick the peak of the hump. And you can calculate the slope, right? In this case, it's called the gradient. And you just move in the direction of the gradient. So I go from there, and I move in the direction of the gradient, and it says, go to that point. Then I go to that point, and I calculate the gradient, and then the gradient tells me to go to that point. And I do the same thing, and the same thing, and eventually you find your way into that groove, that local minima, right? So not very difficult to program gradient descent. Beautiful algorithm, which is very powerful for a data scientist. So in any case, right, this is now sort of demonstrating that even I can fit the 2 parameters of that line if I choose to. Don't worry too much about understanding this slide. It's for those who actually want to go and try to implement gradient descent. This is the only thing you need. It's a one-line algorithm. It's this. Right? Choose a random theta, and then just do theta minus some parameter alpha times the gradient. And you're just basically saying, this is basically just saying, pick a random point on the curve, and then move in the direction that the gradient tells you to, and then repeat that process. Right? Until somehow you're not moving anywhere. Eventually you'll find out that you're just sort of like walking around the bottom of that. Right? So you have to have some type of tolerance. If you want, I've worked out gradient descent for the 2 theta problem. Right? So it's there if you want to try to implement it. Those are the 2 partial derivatives that you'll need. I've calculated them for you if you don't know how to calculate partial derivatives. But you do. If you know how to calculate a derivative, you know how to calculate a partial derivative. Okay, so here I've implemented gradient descent on the simpler problem, like this sort of pinwheel. And I can show you how it works out in theory, well, and in practice. Because like I programmed this in Python with an honest-to-God example. I gave it this scatter plot, and I said, okay, run a line through 0, 0, give it 0 slope. Right? So it says, okay, your line is associated with cost 116.3 at your first iteration. Come on, run one iteration of gradient descent, and it tilts it a bit. It says, okay, I've went in the direction of the gradient to minimize cost, and your new line has a cost of 75.8. Come on, gradient descent again, 18.3. For a third time, 8.8, 7.8, 7.6. Right? So you're just going to basically like do this, 7.8, 7.6, right? Eventually your algorithm is just going to stabilize somehow. It's not going to fully stabilize, right? That's why in the last assignment we asked you to come up with this tolerance function, right? We just care that the answers are like close enough, right? That's called a tolerance, because this is just going to wiggle infinitely at the end. It's never going to return the same thing due to numerical error. This is the general gradient descent algorithm. I've given you the ith partial derivative if you want to go implement this. This looks more scary than it is, right? All this is a sum. Right? You're just summing something. Right? Given d, just add these numbers together in the manner that I prescribed there. Okay, so that's linear regression. That's the easier one. Okay, so linear regression was given a plot of points, fit a shape, a line through those points, which somehow allows us to predict where points should be. Logistic regression is different, right? So in linear regression, the labels could be anything. They're house prices. You can have an infinite number of house prices. For logistic regression, I'm going to restrict our labels to off, on, true, false, 0, 1, in, out, right? Logistic regression is going to be a predicate, right? But in a predicate in a different way. So I'm going to give you pieces of data, collections of data, and I want to divide the data into separate categories. And then I want a hypothesis function that answers this question. Given a new piece of data, how certain are you that I should be putting it in this box, in this category? And it should say, I'm 60% sure it should go over there, right? So I want to train some type of hypothesis function which is going to tell us what the confidence of putting something in a certain category is. The canonical example for this question is that of labeling handwritten digits. Just for fun, I want you to think about how you would solve this problem. So you guys know what a bitmap is? It's a 16-bit by 16 pixel by 16 pixel image. So 256 pixels. Do you guys know what a pixel is? Thank God. Okay. So you can just think of the number 9 as a matrix of white and black squares, right? That's what a bitmap is, right? So it's data that I can give to you as zeros and ones, right? So I could give you an assignment question that's like, given this 0, 1 matrix, determine if this is a 3. How would you do it? How would you program Python to detect a 3 from a bitmap? That's not possible, right? There's no rule that governs how a 3 is written, because someone's 3, like your 3 may be different than your 3, which is different than a 3 that a 4-year-old would write with a crayon. Some of your 3s have loops. Some people draw 3s with 2 strokes. It's impossible. You're never going to be able to do it. Which is why I wanted to give it to you and see all you guys panic a bit. But I think you find that less fun than I do. All right. So the new problem definition is like this. So this is the whole point of labeling. someone actually has to go out and say, here's a 9, here's a picture of a 2, here's a picture of a 3, here's a picture of a 7. Some human has to go and label all the data. Right? And then we give all of that labeled data to the computer. Right? So our new inputs are bitmaps. Our new features are the black-white information in the bitmap. The new labels are digits, right? Which is telling you that the number 9, that the drawn number 9 is in fact the digit 9, that this drawn number 2 is in fact the digit 2. Right? And our data is now just going to be the pairings of the bitmap and what the bitmap is representing. So in this case, our hypothesis function is going to work like this. We're going to give it a bitmap. We're going to give it a set of parameters that we're going to learn. And then hopefully, if I ask what's the probability that this handwritten 3 is in the 3 category, parameterized by theta, it better be better than a half. Right? There's no point training a function which tells you, okay, imagine how useless this would be. I have 2 categories, and I ask you, what's the chances that this is in this category? And you say 50%. That's not useful information, right? Without any prior knowledge, the probability that it should go in either one of these is 50%, right? So the hypothesis function you give me better be telling me that something goes into a category with probability better than 1/2, right? Otherwise, there's no point showing up. Can anyone guess who invented this handwritten technique? Who would have a huge amount of incentive to automate reading digits? Banks was what they guessed in the first class. It's wrong, but it's a good guess, yeah. U.S. Postal Service, right? When you write a letter to someone, you're writing in the address with your pen, right? And they literally had to get someone to read it. So back in the 70s, some guy invented this technique to detect handwritten digits. This has been around for like 40 years, and I don't know why it's made such a resurgence. I know why it's made a lot of resurgence. We have a lot of data. Because we all give all our information to Facebook and Google happily, right? Because they let us use their email service for free and let us creep on one another at night. Okay, so here's how I want to describe the problem visually. Right, so I can give you a bunch of pink points and I can give you a bunch of blue points. You can look at them and say, yes, those are 2 different categories. But to have a computer look at this and go, yes, that's 2 different categories, this is an entirely different question. So now I'm going to give you the mathematics for telling a computer that those are 2 different categories. So what we want to do here, okay, it's going to be very similar to the linear regression. Why? Because I want to separate these 2 categories with a line. Right? And this line is going to be called the decision boundary. Right? So basically, we're going to be training a boundary. We want to look at our data, and we want to just separate it using a line. And this line, in this case, you need 3 parameters. Right? This is the more generalized line. I could simplify it. So the first line I gave you through the pinwheel is the line. Right? You can also have a line which moves up and down, which needs 2 parameters. But strictly speaking, because you're used to writing a line as y equals mx plus b. You ensure that the thing you put on y is 1. Generally speaking, that's not the case. You have a times y plus b times x plus c. That's the general line. Right? The general line has 3 parameters. Right? So that's why I wrote it with 3 parameters on the board, the fully generalized line. So here's the question now. Right? So I have a hypothesis function which basically can cut data into 2 pieces. But the example I gave you was that of categorizing the digits 0 through 9. So my question is, can I use how can I use one decision boundary to categorize 3 things? Any ideas? I just ask these questions so I can drink coffee. It's easier than you think, right? So I can categorize into 3 pieces by yeah? No, still with lines, I'll do it 3 times. I say, okay, one decision boundary for being included in pink or not. Right? So one hypothesis function for you're in pink or you're not in pink. Another hypothesis function for you're in green or you're not in green. Another hypothesis function for you're in blue or not in blue. Right? So we can separate the data many times into 2 pieces and then use all of that information to to isolate what category it really is in. Okay, so now I'm going to have to use some sort of math that maybe you haven't seen, right? Because our new hypothesis function has some restrictions on it. So given that our hypothesis function is a probability, 1, the hypothesis function needs to return a value between 0 and 1. Right? It's a probability. I can't give you a probability that's 2.7 or negative 1. Second thing, if I'm guessing good, the hypothesis function should tend to 1. Right? Like if I'm certain that something is in a category, the hypothesis function should be like, yes, assign that a high probability. And if something is bad, right, if something is uncertain, then I should guess wrong. Right? So I'm going to draw a picture. That's the boundary. And I have a point here, and I have a point here. Which point would you be more comfortable rendering a decision on? You're much more sure that this is in the category than you are that this is in the category, than you are that this is in the category, right? So strictly speaking, the further away from the boundary you are, the more positive we can be that you're inside the set. And the closer to the boundary you are, the less confident that we are. So our hypothesis function is going to need to account for this, right? That if you're closer to the boundary, that our confidence level should drop. So we have this thing in mathematics called the sigmoid function. 1 over 1 plus 1 over e to the z. It looks like this. Why do I like it? Well, it has all the properties that I just asked for on the page before. In both directions, well, in one direction it tends to 1, in the other direction it tends to 0. Right? So we have that. So what I'm going to do is I'm going to use the sigmoid function, and I'm going to let the sigmoid function take this distance. Right? So the further away you are from the boundary, the greater the distance, and the closer to 1 you get. The closer to the boundary you are, the smaller the distance, and the closer to 1/2 you are. Right? So this function's doing exactly what we need it to do. Right? You shouldn't be understanding this immediately. You may have to go back and look at it. This is just sort of the most superficial exposure I can give you to this. So this is a picture explaining basically what I just explained up here. Who knows what a dot product is? Do you guys not take linear algebra in high school? Oh boy. Should start studying it now then, because you're going to be for a shock. You're going to need it.
It's also in vectors, right?
Pardon me? Oh, they might have renamed the classes since I've taken them. I was old cohort.
Yeah, linear algebra is vectors.
Yeah. Okay, so vectors, whatever. Did you guys ever answer this problem? Given this point and this line, what's the distance from the point to the line? Yeah, that's called a component. That's what we need to do this. Right? And it turns out the component is given by the dot product, this. But what's this dot product? It's the line. Right? You can describe a line as the dot product, right? Its slopes and its point. Right? So we're using linear algebra here to solve these problems. So I'm giving the sigmoid function basically the distance to the line. And it's going to do all those things that I just described. And so the point is, as your point approaches the boundary line, the probability, like the certainty that it's in the category is approaching 1/2. Right? Which is the worst that it can be. Right? If I was 0% positive that it was in this category, that is 100% positivity that's in the other category. So the worst probability in this case is 1/2, not 0. Okay, so I'll tell you a little bit about the cost, right? But what do we need our cost function to reflect? Okay, because we have two things here. I'm saying you're giving me an object, and I'm rendering two guesses on it. I'm saying this object belongs to this category, and I am this certain that the object is in this category. So you're giving me a category and you're giving me a confidence. So there's two things that I have to minimize here. So when we have a cost function, if I'm making an incorrect guess with high confidence, that should be penalized a lot. If I'm making a if I have a correct guess with low probability, that should also be punished, right? And then we're going to be able to minimize this cost function to find the best decision boundary. So you can think about this a bit. You just use ln, right? Because ln goes to infinity at 0 and tends to 0 at 1. This is perfect, right? So this will infinitely penalize bad guesses and reward good guesses. You just have to think about it a bit. I don't have enough time to really flesh this out. But suffice it to say, we can create a cost function with the desired properties that I just mentioned, which ends up being convex, right? Which is amenable to this gradient descent. That's in detailed how you set up the cost function if you're interested in coding it. You're going to also need this proposition, right? Because I need to tell you what the gradient is. So this is a statement for getting what the gradient is. I'm not going to prove it because it's super boring. Plus, you probably don't need it. But if you want to implement gradient descent for this problem, this is the slide that you need. Okay, now I can show you visually what's happening, right? So I have two categories, the pink category and the blue category. And I went to Python and I implemented all of this. And I said, let's look at the decision boundary that's like just the line on the x-axis, the line with 0 slope and 0 y-intercept. And it's going to say, okay, that's a pretty crappy decision boundary. It has cost 72. This is slower, right? I let gradient descent run 50 times, and it refines my weights a bit. And it says, okay, this is better. Your cost is 16. I let it run a bit more, right? 100 iterations. It says, okay, better. Cost is 13. 150 iterations, cost is 11. 200 iterations, cost is 9. 250 iterations, cost is 8, 7, 6, 5, 5. Right? So it seems that at iteration 400, nothing's changing. Right? We've found a stable decision boundary. Right? So these lines were legitimately generated by the gradient descent algorithm. I didn't, like, this isn't me inventing this. I took the actual values out of the algorithm, and this is what it was doing. Okay, but what happens if we want to divide more sophisticated types of boundaries? Right? So like what happens if all of my blue points are inside the interior of a circle and all of the pink points are on the outside of the circle? Okay, so one thing I should mention. We already have the power to do this, right? So just because we have a line, so we've been working with lines, right? So we have some line that looks like this. Like this in the computer is just going to be stored as a bunch of numbers. Right? These numbers and then these numbers. Right? You're not actually storing an equation. Python doesn't have the power to describe arbitrary polynomials. So we can just make a different agreement. We can just say, okay, we have theta, then this, right, then this. Okay? You can just say, oh, okay, well then just take these weights as like the coefficients for higher order polynomials. But the problem is, if I have two variables, like in this case, a circle. So a circle needs two variables to be described. It's x squared plus y squared equals 1. But how many terms does a polynomial in two variables of degree 2 have? Well, constant term, x, y, xy, x squared, y squared. Right? So that requires 6 terms. If I go to a cube, this will exponentially increase the number of terms that we need here. Right? So what I'm just trying to get at is, despite having the technology to make this work, practically speaking, it's not going to work, right? Because the number of terms that we need to train it will explode, right? It's just the problem's dimension is too large. Okay, so why do we care? The neural network is a solution to this problem. A neural network allows you to train an arbitrarily complicated decision boundary through points. And it allows you to do so efficiently. Now, in the last 10 minutes, I want to be able to show you at least one neural network. In order to do this, I need to show you this picture. This picture is going to be something you'll be quite well acquainted with if you continue in computer science. We are obsessed with networks and graphs of this type. What you need to know about a graph. The circles are things called nodes. The nodes are connected to each other with blue lines called edges. And these edges have weights, which I've imposed in the middle of the line. Right, so what I want you to see here is, so this is called the node, or a neuron. And the reason it's called a neuron is because there's a direct analogy to how our brain works. Your brain is an amazing wet computer. Right? You have built-in image recognition and training. Right? Your brain can do amazing things that a computer is hopeless at. Right? So it's fairly amazing how everything in here works. We have very little understanding of how that happens. But anyway, so this is sort of the mathematical implementation of the idea behind your brain. Are any of you studying psychology? Like, so when you memorize something, you're basically just running a neural pathway over and over and over again, right? And when you run the neural pathway, it's like, do you know when you walk around campus and there are like the concrete pathways and then the pathways that students create because it's the fastest way, right? It's actually called the desire path. And the best way to design a university is to let the students create the desire paths and then go pave all the desire paths. But that's basically how your brain works, right? You could just, if you try to memorize something, if you repeat a phone number again and again and again, you're running the same neural pathway, which is going to strengthen that neural pathway and then form a memory, right? That's, in a nutshell, that's what we're doing with logistic and regression. Right? We're just doing something over and over and over and refining a set of weights. This is how I can draw linear regression as a graph, right? You give me a set of inputs, which are weighted, and then I make a calculation, right? So this basically is how I can visually represent this formula, right? This is the whole linear regression procedure. Right? Given some inputs, these are the slopes in that case, and then you just look at what you get, right? So that slide basically is just a way of describing this computation. Right? It's just saying this, get that sum, right? But the reason I want to draw it like this, well, okay, you can also do the same thing for logistic regression, except the logistic regression has to take this and then give it to the sigmoid function. Right? So that's why I put in that node, right, that this node is going to collect that sum and then apply the sigmoid function and then throw out the value. This is a neural network. This is a 3-layer neural network with one hidden layer, right? And what it is, it's just basically a description of what computations that you need to sort of implement in your computer. You need to be able to take n input vectors, or n inputs, right? One vector of n elements. So this says that x1 gets sent to these three nodes with a weight, right? So this is going to say, it's going to find the individual probabilities. So you give it a bitmap, and it's going to calculate the individual probabilities. What is the probability that it's in category 1, in category 2, in category 3? And then the last thing is just going to choose the largest one of those. Right? So this is a neural network that allows you to categorize 3 digits. Or maybe allows you to categorize 2 digits and then the rest. Right? You could get 0, 1, and not 0 and 1 from this. Right, so, but fundamentally, all this is describing is like a bunch of linear algebra. Right? It's just telling you, it's just a description of what matrix operations to do when. This is a bigger neural network. Right? You can make these things arbitrarily sophisticated by adding more layers and adding more nodes. Right? And this is sort of what you'll learn in data science, right? Like how to balance these things. Like when should you increase the number of layers? When should you increase the number of nodes? But basically, a neural network is just a huge description of what things should be getting what is input with what is weighting, and then how you should act on that. Right? So when you see that, this is just basically describing a super complicated formula, right, in a compact way. This is the slide that you need in order for understanding what goes in and out of a single node. Right? So if you wanted to go and implement this, you should study this slide a bit. Because this is the slide that tells you how to convert everything into matrix operations, right? Because as you see at each layer here, we're going to have a lot of weights, right? So you need to know what weights to use for what. Okay, so the very last thing I want to tell you today before we go is how then, right? We need to duplicate the process of, so what did we do with our hypothesis function earlier? Well, we said, okay, pick a line, set it, calculate the error, right? So we need to be able to do 2 things. Evaluate our data set on our hypothesis function, and then evaluate the errors that introduced. We need to do the exact same thing on a neural network. And the words for this are, right? So to evaluate, to give something to the input of a neural network and to get the output, that's called forward propagation. So we're moving forward through the network. That's easy, right? It's basically just doing arithmetic, right? As I described. Now, the beautiful thing here is something called backpropagation. And I'll just give you a little bit of it, and then I'll let you go enjoy your Thanksgiving. Right? But basically, you can give an input to this network. It will forward propagate and say, okay, given this input, I guess that it's this. And then you can ask, well, how wrong is your output? And then it could say, I'm this wrong, right? So if I'm wrong here, I can say, well, how much, if I have an error here, how much of that error came from this node? And then you can say, a lot of error came from that node. Then you can say, well, then weight it down, then punish it. I want to take less of its contribution. And then you can go to here and you can say, how much error was introduced at this node? And you're like, well, a lot. Okay, well, specifically, how much came from here? And how much came from here? And how much came from here? And then you can say, well, then downrank those, right? Like anything that's contributing error, lower the weight. Anything that's contributing a correct result, increase the weight. And this is training. This is what's happening, right? So you take an input, you forward propagate, you find the error, and you back propagate, right? You adjust all of the thetas, and then you forward propagate again, and you should get something better, right? But you still have error, and then you use that to back propagate, to reweight all your functions. Then you forward propagate and back propagate, and forward propagate and back propagate. You do that as many times as you can. And then eventually, the weight should stabilize. And there you go. That thing that you're left with is going to be a neural network which is categorizing for you on some problem, right? So it's really not that magical, right? It's just linear algebra, right? Linear algebra and a ton of data, and magic happens. It's a good practice problem to implement logistic regression for these labeled digits. It's very satisfying to see just how quickly. You don't even need a big data set. I think with 500 you can already write a pretty effective digit recognizer. So you don't have, none of this is testable. Remember, don't freak out. This was just for enjoyment. Otherwise, you guys have a very safe and pleasant Thanksgiving. 31 degrees tomorrow. Bring shorts with you, or you'll regret it. Right? That's what they say. Right? I'll put them on the website. Yeah.